Hello everyone, my name is Rajat Dhama and I will be presenting today on the topic of graphene and its role in spintronics. In this presentation, we will discuss the structure of graphene, properties of graphene, applications and the introduction to spintronics, the principle, the advantages and finally the role of graphene in spintronics. Graphene is a pure carbon in the form of a very thin, nearly transparent sheet which is only one atom thick. Technically, we can say that graphene is a flat monolayer of carbon atoms tightly packed in a two-dimensional honeycomb structure. It is regarded as the first 2D crystal and the thinnest ever material created in the world. It is obtained from graphite, hence the name graphene, which is simple and abundantly available form of carbon. It was discovered by Andrei GM and Konstantin Novoselov in 2004, and these scientists were later awarded Nobel Prize in 2010 for the discovery of graphene. It is a super strong and stiff, amazingly thin, almost completely transparent, extremely light and an amazing conductor of electricity and heat. Graphene has a hexagonal pattern. It has a single planar sheet of atoms with sp2 bonded carbon atoms densely packed in the honeycomb crystal lattice structure. It is stable due to a tightly packed periodic array of carbon atoms and an sp2 orbital hybridization, a combination of orbitals px and py which constitute the sigma bond. Graphene has 3 sigma bonds and 1 pi bond. The final pz electron makes up the pi bond and it is key to the half-filled band which permits free moving electrons. Graphene is self-healing in nature. That means that graphene can self-repair holes in its sheets when it is exposed to molecules containing carbon such as hydrocarbons. Coming to the physical properties of graphene, it is the thinnest possible material with a 2D crystal structure. The density of graphene is 0.77 milligram per meter square, and it is very strong material with the strength of 42 Newton per meter, and it is around 1000 times stronger than steel. It is almost transparent and it has the ability to absorb only 2.3% of the light falling on it. It is a very flexible material which has many widespread applications. Graphene is a zero-gap semiconductor because its conduction and valence band meet at the Dirac points. The Dirac points are 6 locations in momentum space on the edge of the Brillouin zone, divided into two non-equivalent sets of 3 points. 4 electronic properties which separate it from other condensed matter systems are electronic spectrum, which means that electrons propagating through graphene's honeycomb lattice effectively lose their mass, producing quasi-particles that are described by a 2D analog of the Dirac equation rather than the Schrödinger equation for spin half particles. Second unique property is electron dispersion, which is given by the equation provided here, where the wave vector k is measured from the Dirac point. The third property would be single atom wave propagation. It means that the electron waves in graphene propagate within a single atom layer, making them sensitive to the proximity of other materials such as high K dielectrics, superconductors and ferromagnetics. Experiments have shown that graphene has a remarkable electron mobility at room temperature in excess of 15,000 centimeters square per volt second. Also, the symmetry of the experimentally measured conductance indicate that the hole and electron mobilities are nearly the same in graphene. Graphene sheets are said to have an electrical conductivity 10 times that of copper. Graphene is the most reactive form of carbon owing to the lateral availability of carbon atoms due to its 2D structure. It has the highest ratio of edgy carbon atoms in comparison to similar materials like carbon nanotubes. It burns at low temperature, for example 350 degrees Celsius or 620 Kelvin. It has unexpectedly high opacity for a single layer structure, which is a consequence of the unusual low energy electronic structure of monolayer graphene. Such unique absorption could become saturated when the input optical density is above a threshold value. Due to this special property, graphene has wide application in ultra-fast photonics. Graphene has a high carrier mobility as well as low noise, allowing it to be used as the channel in a field effect transistor. Graphene strongly interacts with photons with the potential for direct band gap creation. This is promising for optoelectronic and nanophotonic devices. Potential uses include transparent films, touchscreens, etc. Graphene could solve a major problem for fuel cells, fuel crossover that reduces efficiency and durability. Graphene layers could also be used to extract hydrogen gas out of the atmosphere to power electric generators with ambient air. Due to extremely high electron mobility, graphene may also be used for protection of highly sensitive Hall effect sensors. Potential application include sensors for DC current transformers used for spatial applications. Finally, graphene is claimed to be an ideal material for spintronics as it can support electron spin to very long distances at room temperature. Coming to the topic of spintronics. Spintronics is defined as the study of the intrinsic spin of the electron and its associated magnetic moment. In addition to its fundamental electronic charge in solid-state devices, there are limitations to Moore's law, as we all know. Moore's law states that the number of transistors on a silicon chip will roughly double every 18 months. But now the transistor and other components have reached nanoscale dimensions, and further reducing this size would lead to scorching heat, which will make the circuit inoperable, and the quantum effects which come into play at nanoscale dimensions. The main advantage that spintronic devices have over today's electronic devices is the fact that unlike electronic devices, they do not only use charge of the electrons but also their spin to store information, which is why they are significantly more efficient. In spintronic, the information is carried by the orientation of spin rather than the charge. Spin can assume one of the two states, spin up, spin down. These states, spin up or spin down, can be used to represent 1 and 0 in binary logic. In certain other materials, spin orientation can also be used as spintronics memory, as these do not change when the system is off and hence is non-volatile in nature. There are numerous advantages of spintronic devices. They have low power consumption, less heat dissipation. Spintronic memory is non-volatile. It takes up lesser space on a chip for a spintronic device, and thus it is more compact. Spin manipulation is faster, so there are greater read and write speeds. Performance of a spintronic device improves as the devices go smaller. Spintronic does not require unique and specialized semiconductors. Switching time is very less compared to the normal RAM chips. Spintronic RAM chips will increase storage densities by a factor of 3, and they have faster switching and smaller rewritability rates. Before looking in spintronics and graphene, it is worth noting that spintronics is already established in one critical area of digital electronics, namely data storage. Spin can be thought of as the rotation of the electron around its own axis in two orientations, up and down. Combine these magnetic orientations with the on-off current states in binary logic, and we have a system of 4 states with the two magnetic orientations forming a quantum bit or qubit. In computing technology terms, 4 states rather than 2 provides for higher data transfer speeds, increased processing power and memory density, and added storage capacity. Electron spin provides an additional degree of freedom to store and manipulate information. The read heads of modern magnetic hard drives exploit the spin-related effects known as giant magnetoresistance and tunnel magnetoresistance. In both the cases, the result is a magnetic field sensor that may be used to read data magnetically encoded in hard drive platters. Magnetization of graphene. Graphene, in its pristine state, is a strongly diamagnetic material, and creating a magnetic order in it is a major challenge. However, it is very vital to induce magnetic moments in graphene if it has to be used in spintronics. It could be achieved through the defect in the material's hexagonal crystal lattice structure or by the influence of absorbed atoms on its surface. One of the methods of magnetizing graphene is by hydrogenation, in which hydrogen atoms chemically absorb onto the graphene layer in a reversible manner. This creates an imbalance in the crystal lattice, thereby inducing a magnetic moment. Graphene is a promising material for spintronics applications as it can support electron spin over very long distances at room temperature. It also has very high electron mobility and a tunable charge carrier concentration. Earlier experiments to transport electrons in graphene showed a low spin injection efficiency of around 10%, which could have been due to conductance mismatch between metals and graphene. But later, higher efficiency was achieved by using magnesium oxide films as tunnel barriers. Maximizing spin lifetime of an electron is critical when it comes to applications of graphene spintronics. Spin transport in graphene will only prove useful if we can achieve spin lifetime of nanoseconds and higher. Two mechanisms have been proposed to explain experimental trends, and both of these mechanisms have their origin in metal and semiconductor spintronics, and they each rely on spin-orbit coupling. Spin-orbit coupling is the interaction of an electron spin with its motion, which leads to shifts in the particle's atomic energy levels as a result of the interaction between the spin and magnetic field. However, recent studies have shown that the electron mobility is not the limiting factor for spin lifetime, and the scattering and impurities are not primarily responsible for spin relaxation. Hence, determining the primary source of spin relaxation is an important challenge for research on graphene, and if we can identify it, it will help raise spin lifetime in graphene towards the theoretical value, which is around a microsecond for pristine graphene. Graphene's ability to maintain the spin of an electron over a long distance has made it very useful in the field of spintronics. Spintronics provide an alternative way to solve the problems which arise due to limitations of Moore's law. The spin of the electron has attracted renewed interest because it promises a wide variety of new devices that combine logic, storage, and sensor applications. However, there have been a lot of limitations in the use of graphene in spintronics, and there has been a lot of research for making it more efficient and usable in devices. In my view, the reality is that graphene in spintronics is a maturing field of applied science and engineering, which holds a lot of potential for the future electronics. That will be all for graphene and spintronics from my side. Thank you for watching my video, friends. Your views are welcome. Thank you.